Although there are 3p's are there, but all those 3p and like p and s orbitals are there, but they are involved in sp3 hybridized orbitals. So now water has no other vacant space. But that is different in case of silicon, germanium, lead, and tin. They have empty d orbitals, so they can destroy the compound in a stepwise manner. Okay. So like that. And as I was just telling you, right? Remember that this CSR question actually. Very, very important question. Please take a note of this. SiF4, for example, SiF4, now other way around. Silicon can react with, look at this. Silica, sorry, not silicon, silica, you see, silica only soluble in hydrogen fluoride, only soluble. It is absolutely a fact, right? Only soluble in hydrogen fluoride, which is one of the strongest acids that known. And how does it react? SiO2, HF, I told you that. If there are fluorine and oxygen is there, silicon takes fluorine atoms. So it's because, as I just now said, so the silicon fluorine bond has high enthalpy. So it forms a is not used wrong. SiF4, tetrafluorosilicon. Silane, how to say, like one can always write like this. Right? This tetrahedral. Why is it so stable? It's because, as I said, right, there is a back bonding from every fluorine to silicon. That is P to D. Right? There is a partial, it's very, very partial double bond, right? So that's what this compound is stable, which gets converted to SiF4. Now, SiF4, what is the byproduct here? Water is a byproduct. And SiF4 again enemy to water, right? So immediately water, it acts as a like 2H plus. So it forms a fluorosilicic acid. This is the main reason actually. This conversion leads to H2SiF6. This is fluorosilicic acid. That is why this compound is not stable. So this is very important question, my friend. Take up this as a mid-sem, could be question. This is fluorosilicic acid, H2SiF6. Okay. So what is the fluorosilicic acid? Can someone tell me what would be the silicon oxidation state here?
Sir, +4.
Yeah, exactly. Right? Yeah, it's simply +4. Silicon cannot oxidize. Okay? It's only silicon cannot form +5, +6. Why not? It cannot form +5, +6. Right? You can only remove 4 electrons maximum, outermost. You cannot remove another electron. So that's what +4 is the highest oxidation state that you can reach in case of silicon. Right. Okay. What is the geometry at this one? Actually, no. What is the real formula of this compound? It's like acid. It's strong acid, one of the strong acid. This like this 2H plus and SiF6 2 minus. Do you agree with me? Just like hydrochloric acid, it can dissociate into like this.
Yes.
2H plus and SiF6 2 minus. So what is SiF6 now? SiF6 is a, see why this compound is very stable, very, very stable actually. This compound is, why is it so stable?
So because d orbitals are filled up by fluorine. Yes.
That's here for sure. And also it is a octahedral. Octahedral, no? Homoleptic octahedral geometry. It's very, very stable. In octahedral, many compounds are highly stable because of the geometry, lowest energy, highly symmetric, right? Octahedral also is quite symmetric. One of the stable symmetry octahedral. Right? It's because of this. It takes up an octahedral geometry, which 2 minus ion. It's a silicate, fluorosilicate actually. Simply fluorosilicate. Okay, it's a fluorosilicate anion. You know, question can be twisted in another form also, my dear friends. What happens here, if you treat this with some salts, it can also form salts, for example, Na2SiF6, sodium fluorosilicate. Okay, so this is what hydro. Can you tell me what is the name of this H2SiF6? Please practice this. Hydros, how do you say this name? Hydro fluorosilicic acid. Silicic hydrofluorosilicic acid is an acid. It's a Is it dibasic acid or diacetic acid?
Dibasic.
It's a dibasic.
Yeah,
Dibasic acid.
to get clear. So like this, remember this, practice this. It's very, very important. Interesting question. So this is what now? Hydrofluorosilicic acid or fluorosilicic acid. People also write simply fluorosilicic acid. So what is the reaction between SiO2 and HF? It forms H2SiF6 in presence of water. Okay. Yeah. And then yes, sorry. Yeah. We have seen other hydrates in periodic table of elements, as I had discussed already, right? Sorry. Yeah. So these you can see in a group 14, all these hydrates. So down the group, all these hydrate bond becomes more covalent side, ionic side rather covalent side. So those things need just to say about it. And is it anything important to discuss? Not really. Let me go ahead to the next this ones. Okay, so this is a bit interesting, in my opinion. Silicates. Pen. Silicates actually. In silicates, silicon forms n number of oxides like carbon dioxide. Carbon oxides are what? Carbon forms oxides, carbon dioxide, carbon monoxide. So like this, carbon cannot form many oxides, only few. But in case of silicon, silicon forms lots of oxides. In all these oxides, the main unit is silicate. Okay, you see that this is called silicate. SiO4, 4 minus. And now what is the, again, geometry at silicon here in this case? Tetrahedral. Okay, so like this one, you can see that silicon, all 4 hydrates, oxygen atoms are arranged in a tetrahedral geometry. Now, what is the hybridization of silicon and this silicates? It is simply sp3. Okay, sp3 hybridization. Why is it sp3? It's because of this one. We have now again, as usual, just like SiF4, right? SiF4 I said tetrahedral geometry, because all the CCl4. So see here we have 3s2, right? Remember, we have 3s2. This is ground state 1, 2. In excited state, this s electron will go 1, 2, 3, 4. So these guys, all these mix and form hybridized sp3 orbitals. Right? That's what silicate prefers to have tetrahedral geometry with sp3 hybridization. So silicates are different types, right? Different types of silicates are there: cyclic silicate, chain silicates, pyrosilicates, orthosilicates, sheet silicates. Means depending upon these SiO4 units, they interact with each other and forms macromolecular structures. Depending upon their interactions, okay, and they can be called cyclic. Lots of cyclic compounds. And chain, for example, as I said, chain silicates. Chains like chain like this. And pyro means Oxygen bridges like this. There are so many like this. Orthosilicates, like orthosilicates are simply like discrete silicate. They are not like bigger macromolecules. And lots one is sheet silicates. Sheet like sheets, like like you have book, right? Or graphite. Graphite, the silicates, like it forms a sheet like silicates. So we don't need to worry about for this course all this information, but try to know that what are the different silicates which are possible. You should be able to answer that: cyclic silicate, chain silicates, and etc. If you want more information, maybe you can go through housecraft, how really existing, how they are stable, and etc. So, for example, here,
Sir,
silicate, yeah,
sir, why silicon forms different oxides but not carbon?
oxides of silicon. Yeah, no, I told you that in case of silicon, what happens in case of carbon? For just imagine, carbon cannot form. Just imagine CO4 4 minus. It is not possible. Now carbon, oxygen, 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 oxygen. Right? This is not possible tetrahedral. It is number one, right? Number one. Um, what is it? Like no, I mean to say CO4 4 minus can form, but it cannot form this kind of oxides, silicates, and etc. etc. It's because um, we have the oxygen. In case of silicon, why is it possible? Let's see how silicon it is possible, but in case of carbon it's not possible. Because in case of silicon, you can see that, right? Silicon has empty d orbitals. Oxygen has lone pair of electrons. It can only give to other side.
Okay.
It can also does other side also, because other side silicon is there. So like this, that like extend the structure like towards you, towards me, towards like 3D. Wherever oxygen atom is there, anywhere close by silicon atom is there, they form a bond, or some sort of interaction. That is impossible in case of carbon. But in case of carbon, you have
Okay.
graphite. Graphite is like a layer structure, and
Yeah. Sheet like.
diamond. Diamond is not layer structure. It's
Yes.
tetrahedral geometry. Tetrahedral it is 3D structure, just like SiO2. SiO2 like a macromolecular structure, 3D structure, similar to the graphite. Look at graphite. Sorry, diamond. Diamond is also sp3. All the three sides extended. That's what the graph. Diamond is a rock, highly stable, solid. Right? It's because of an extended molecular geometry. Graphite is not like this. Graphite like a 2D sheet. It's quite reactive. Graphite is much reactive than reactive material than uh, uh, like diamond. It's
Diamond.
because of the geometry. What kind of, for example, graphite? Uh, what is the hybridization in graphite? Can someone tell me?
sp2.
sp2, right? Means there are pi bonds, lone pairs, and etc. So that's what it's reactive. Just like alkane and alkene. Alkenes are highly reactive. You
Yes.
can hydrogenate them. Similarly, graphite is more reactive because of the sp2. But now go to the diamond. Diamond is totally sp3. All orbitals are occupied, and it's a 3D structure. It's rock. That's what you need to have a. People use a diamond to cut other some sort of materials. So such a rock, very very stable bonds, carbon bonds. Okay, I hope it is clear.
Okay, sir.
Yeah. So okay, all these like silicates contain zeolites and etc. Right? These are different silicates. You can see, as I said, and zeolites are also naturally occurring. So in zeolites, actually, silicate moieties are one of the part of the zeolites. Okay, you see that how these zeolites contain silicon oxides, oxide materials. You see that, right? How these what is that? Yeah, discard. Yeah, you see all these guys, no? They form an extended structures with small holes into that. No? So these zeolites are used. This is important, my friend. These zeolite silicate salts used for ion exchange reactions as molecular sieves. People also use them as catalysts and catalyst supports. Right? what happens in the geolites, metals are also there. Like, geolites metal also there. So they use for ion exchange reactions. Why ion exchange reactions? You have a hole here. One ion can sit in these holes to remove another ion. So like this, that's what ion exchange. For example, chloride, you want to exchange chloride with iodide. You can use these materials actually. People use it too. Yeah. Okay. So like that, group 14, one would discuss about. If you move on to group 15 now, let's also see a similar differences of group 14, group 15 elements. As we all know, group 15, right? By the way, this is very, very important. Many of us do not know, many on the society. Look at this, right? You see how much nitrogen is there. What we breathe, nitrogen content. If you have a circle, how much percentage this is? 78% of our,
78%.
yeah, what we breathe, what exists in this, like in air is nitrogen, which is group 14 element, group 15 element. Now look at the oxygen, what we are breathing. Oxygen is oxygen. It's only 20% what we are breathing, like this green color. That is group 16 element, right? This is group 16. Carbon dioxide. Carbon dioxide is 0.04%, like almost 1% in the here, right? All other atoms. Organ is also part of here. Organ is highly unstable gas at room temperature and other gases. So remember that the what we breathe, what is the highest element that contains the air what we breathe is nitrogen, not oxygen or not carbon dioxide. Many of us think that oxygen. No, it's not at all oxygen. Oxygen is only 30%, sorry, 20%. 78% is dinitrogen, and highly stable species, dinitrogen, as you all know, right? Nitrogen triple bond with one lone pair of electrons on both sides. Right? Very, very stable. It's a rock stable actually. Okay, so these are the elements of this group. Their abundance, you can see phosphorus among all these elements. If you look into that, phosphorus abundance is more on the Earth's crust because phosphorus forms lots of phosphate salts. Phosphates, PO4, PO4 4 minus, PO4 3 minus, all the salts. But down the group, it decreases. But more than nitrogen, phosphorus exists. But phosphorus exists as a solid. Nitrogen exists as a gas and on Earth's environment. But Earth's crust, phosphorus is more dominant than nitrogen, right? But on the Earth's environment, nitrogen is more dominant. Phosphorus 0. Phosphorus is there means people die. It's not safe. Okay, so like this here also we have to look at. Now I don't look at all of them. Only important ones which are relevant to this course, right? Now look at that. No, as I said, no. You see, this is like you can see, nitrogen single bond is 160 kilojoule per mole. Nitrogen double bond is 400 around. But once you come to the nitrogen triple bond, you should remember this figure, 946 kilojoule per mole. Very stable compound. To break dinitrogen, you need a lot of energy. Now, phosphorus. For example, is it phosphorus? Phosphorus to nitrogen, it is phosphorus double bond is triple bond is very, very weak. Right? You know that because of the size, right? Phosphorus. P2. P2 molecule is highly reactive, but nitrogen molecule is rock. Right? Very, very stable species because of the electronegativity, first of all. Number two, size of the atom, right? You can see the bond. It's almost off, right? Simply almost off. If we now look at that, these two are important for our course. Hydrates, group 15 hydrates, NH, ammonia, and all these NH compounds, right? pH, phosphines, arsenic, HN, etc. So down the group, automatically what happens? The covalent character decreases because of atomic size increases. Number one. Number two, the electronegativity also decreases down the group, right? So that's what also NH is more stable than pH and arsenic H and etc. Right. So other things are trivial. We don't need to perhaps look into them in the deep manner actually. Yeah. Now look at them. hydrates. We all know that ammonia, right? The simplest hydrate of group 15 is what? Ammonia. Ammonia, what is the geometry at ammonia for ammonia? Shape. I don't know. We call it geometry or shape, whatever it wants. What is it? Hey, come on, no, friend.
Pyramidal.
Pyramidal.
Yes. Yeah, come on. You are right.
Trigonal pyramidal.
Yeah, trigonal. Simple say pyramidal. Huh? Don't forget. You should not say negative because ammonia is most simplest. Right? It's not trigonal planar. Remember, BH3 and ammonia. Yeah. So BH3 is what is the basic structure? Trigonal planar. But ammonia is pyramidal. Why is it pyramidal? But why is this trigonal biplanar? Trigonal planar? Can someone justify this statement?
So because of the presence of lone pair.
On
Then
nitrogen.
okay, so what? Then what does it matter?
So
How does it
the
matter?
bond get smaller in size, they get squeezed.
Yeah. Okay. Yeah. So what happens here? You have a lone pair here, right? Automatically the lone pair bond pair, do they repel so great or like no or attract each other?
Repel.
Exactly, right? Lone pair bond pair repulsion is quite high. So automatically the hydrogen atoms are pushed away. But in this case, it's not possible, right? This case, it has to. That's what it pushes to have pyramidal geometry. And what is the hybridization here? sp2. Here, hybridization, it is sp3. sp3, sp3, but not tetrahedral. You can say like in a way tetrahedral, okay? If you consider this as a ligand, lone pair is as a ligand. But lone pair we don't consider as a ligand, right? It's a lone pair. So that's why it's pyramidal actually. It's pyramidal, okay? One lone pair is a top, other two are down. So similarly, here we have pH3, phosphine is also gas. Ammonia is also gas. pH3 also gas. Similarly, phosphine is also pyramidal geometry. Okay, with one lone pair of electron. Okay, so now, so that's what you can see. Between these two, we know, right? Ammonia, lots of organic chemistry, organometallic chemistry, and coordinated chemistry is known. It's because ammonia is between these two, between ammonia and phosphine. Phosphine is very, very toxic. Very toxic. It smells terrific and toxic. Ammonia is also toxic, by the way. But when you smell it, it's not that much, like sensitive to human beings actually. So ammonia is very well-known compound. Ammonium salts are very well-known and all those things. Somebody, sir, you lone pair in ammonia? Yeah, one lone pair is ammonia. Correct. Yeah, there is a lone pair ammonia. Yeah, there, right? Yeah, there is a lone pair ammonia. So yeah, that's true. Thank you. P3 is also one lone pair. Of course, both are same, similar species. So here, just like ammonia, phosphine also forms some good number of organometallic compounds. You can see that now. Like BH3 is Lewis acid, right? pH3 Lewis base because of the lone pair of electrons. So it forms a Lewis acid base adduct. And BCl3. BCl3 is also Lewis Lewis acid, and pH3 Lewis base. It forms a stable covalent bond. Now nickel, tetraphosphine nickel. So like phosphine also forms stable coordination compounds, but these are difficult to handle, right? So that's what you can say that. And now this is the monophosphine. This is diphosphine, P2H6. P2H6 is something like a ethane, like a gaseous structure or a staggered structure. You can see here, right? P2H6, um, P2H6. Now P has, right? Of course, remember every P has lone pair, is it not? Because phosphorus belongs to group 15, right? One lone pair is here, two hydrogen atoms are here, and backside of the board you have another lone pair and two hydrogen atoms. This is like a gash, like adjacent to each, back to back. Now this is staggered. Staggered is now what happened, you understand, right? Just like ethane, you just rotate this guy little more this side, little more this side, and you get a staggered geometry. Now the lone pairs are like opposite to each other. Now between these two, can someone tell me which hydride is more stable? Which orientation is more stable?
Staggered.
Staggered.
Why?
Sir,
Sir,
because
this-
lone pair are
Say
most
lone
apart.
pair
Distance between lone pair
distance
is very much.
increases in
Yeah.
staggered.
Now lone pairs are not like in the same axis. They are like this. The lone pair interaction is now minimized in case of staggered geometry. But in case of like Gashe, it's like they can interact, not interact, they repel more, right? Because of this one. So just like ethane, right? You can look at the ethanes like staggered Gasho or this one. So because of this staggered orientation, it's not like structure. Orientation of diphosphine, P2H4, is preferred in staggered geometry rather in Gaussian. Okay, good. And phosphine. I'll come back to nitrogen in a minute. I think we're also getting late. Getting over. Phosphorus forms n number of compounds, right? That's what I was telling in the class in the beginning. If you remember, white phosphorus. White phosphorus is highly reactive because a presence of lone pair on the phosphorus, and also what is the bond angle? The bond angle is 60 degrees. It's highly strained molecule, very, very strained molecule, right? Higher is the strain in a ring system, higher is the reactivity, right? That you know very well. So that's why exactly white phosphorus would like a wax, wax like solid. It's like a smooth solid, but highly reactive. That is white phosphorus. Now look at the red phosphorus. Red phosphorus like a white phosphorus units, white phosphorus, like P4 unit, P4 unit, P4 unit. They linked by one of the P. In this P, this bond is break. You have to break this bond because phosphorus should not exceed its valence, right? So that is red phosphorus. And similarly, phosphorus has lots of other, black phosphorus, red phosphorus, all those different phosphorus are there. Violet phosphorus. So depending upon their chain structure, chain orientation, they have different, structures are there, right? But mostly well-known geometries are well-known, like allotropes. It's simply allotrope, right? What are the phosphorus allotropes? P2, P4, and P4 n times. So this is diphosphorus, white phosphorus, red phosphorus. And of course, now you have other phosphorus also, as I said, black, blue, violet, all those phosphorus are there. Okay. So among all of them, as I said, right, these are the hydrates: ammonia, arsine, phosphine, stibine, and bismuthine. Okay. Now you can tell me again, as usual, same argument and same discussion. What happens down the group, the hydrate nature? Which hydrate is more stable? Which hydrate is more stable and more ionic? Automatically ammonia,
Sir.
right? Ammonia is more
Yes.
stable and more covalent in nature because down the group, the atomic size of the bismuth is too big, right? So automatically what happens? The bismuth H bond is like this, bismuth and H bond. So it prefers to have more ionic structure, right? So like this. So that we all know that one. Now this is very important in my opinion. These are, all these are gases at room temperature. What do you call ammonia, phosphine, arsine, stibine, and bismuthine? Look at that. Now boiling points. This is interesting. In case of boiling points, see, ammonia is minus 33, phosphine is minus 87, arsine is minus 60, and again stibine is around minus 25. So this you don't worry. Down the group, they don't follow the trend. But look at this. Ammonia is minus 33, phosphine is 87, and arsine is again minus 60. It's down. So why do you think in case of ammonia has highest? It's supposed to be other way around. Ammonia being lighter, it should have low boiling point, but it has high boiling point than phosphine. What could be the reason?
Ionic
It
character.
has, huh?
Sir, ionic character.
No, ammonia has more covalent character. Phosphine has relatively more ionic. Ammonia is purely ionic, no doubt at all.
The hydrogen bonding.
Yeah, it's very simple. That's exactly correct. Nitrogen case, it has high hydrogen bonding, as one of the colleagues said. This has hydrogen bonding actually. Hydrogen bonding is what? Between what? It's written here. You will see somewhere I have written. You can see this here. Intermolecular hydrogen bonding. Inter, right? Not intra. Inter means between two ammonia molecules. You can see that. So one of the nitrogen has hydrogen atom and other nitrogen has lone pair, right? So what is the hydrogen bonding? The hydrogen bonding is NH bond. This NH is what? Not like typical this H. This is simply that the lone pair H, right? So that's what it happens now again. This lone pair is have another bonding with this. This H is this H is connected to another nitrogen. So like that, it has an extended hydrogen bonding. Higher the hydrogen bonding means molecules are quite close. Automatically, you need more like energy to break these bonds, boiling points, right? For example, water molecule. We have in water molecule, what kind of bonds we have? HO, hydrogen bondings are there, right? So what is the melting point of HO? Hydrogen, H2O, 0 degrees C, right? More than that, it will start breaking, boiling, or melting. So like this ammonia is minus 33 is because of the presence of the hydrogen bonding. Okay, what is time now? Are we getting time? Should I stop or what is time now? Yeah. Hello? Are you guys there?
Yes, sir.
Yes,
Yes, sir, it's 9:30.
Okay. You have another class now? Do you have any other class? No, sir. Okay. Well, I will not take now. I will finish with this slide, this last slide for today. This is very, very interesting slide. Huh? You see that? Okay, so here you see that. Let me remove all of that. You see that here we have nitrogen halides, ammonia, and let us go now with nitrogen halides, NX3, right? X can be fluoride, chloride, bromide, and iodide. Guys, this is very, very interesting question. Huh? Can be mid-sem question also. NX3. Again, as usual, NX3 always forms what? Pyramidal. Huh? Just put NX, X, pyramidal geometry. Okay. Ammonia is a hydrate. The NX3, all guys are halogen atoms. Huh? Halogen, like trihalides. Trihalides. We have again the lone pair here, right? Now let us compare. You all know that this is a very good sigma donor, right? Now let us consider NX3 items. NX3. Which one could be good sigma donor between these two? NH3 and NX3. Which is good sigma donor? Which can give electrons easily to metal centers?
NH3.
Why?
NH3.
Why not?
NH3.
Yeah, why not NX3?
Because F is more electronegative, so it pulls.
Yes. Okay, that's good. Huh? Remember, hydrogen is like almost neutral. Okay. The directionality of the bond from hydrogen to nitrogen is always towards lone pair. Okay. Both are same side. But in case of NX3, X is equal to any halide, especially fluoride or something, then like these are halogen atoms, highly electronegative. Rather giving, they take it, right? So this bond is mostly towards X side. And lone pair directionality is other side. Lone pair is always giving other side, right? Sorry, like this. Lone pair directionality is towards giving to something else. Now here, hydrogen atoms also pushes this lone pair directionality to the same side. But in case of halides, the same halides is not like the opposite. One is that side, other one is this side. So automatically, the relative donating power is much lower in case of NX3 than ammonia. So that's what ammonia is a very, very strong sigma donor, but not the other ones. Okay, so that is what NH3 is much strong donor than NX3 species. Okay, so that like that. Now, if you look into among all these guys, which one would be more sigma donor? NF3 to NI3.
NH3.
Sir, NI3.
Sir, NI3.
Yeah, right. I think it's simple, right? Because of the F is more being electronegative. It has more this back bonding, right? Rather I3. I3 keeps that electrons close, right? And also, what are this? For example, Ni3. As I said last time, right? Here we are dealing with different orbitals, right? So this orbital also differences. Nitrogen lone pair is like this, but iodine lone pair is like this. It's also towards more ionic iodide. So the that lone pair is very easily available in case of I3 than NX3. Okay, so like this one can that is here, which is what, for example, see stability, especially of course stability of the trihalides are also like this. NF3 is more stable, NCl3 and Br3. And Lewis basic strength, as you answered just now, Ni3 is more Lewis basic because of the decreasing electronegativity of halogens. And bond angles in case of PF3, PBr3, like PA3, because PA3 I bond is too big. Iodide atom is too big, so the bond angle also increases a lot in case of PA3. Then PF3. PF3 is a very well pyramidal geometry, but PA3 is more like a bulgy because iodine atoms are too big. So something like this. P like this, for example, iodide atom, iodide atoms, and iodide atoms. These are too big, right? Automatically, this bond angle, what happens? It should be more, right? It's more than a typical angle in any pyramidal geometry. Okay, so I think that's enough for today. We will meet again in the next class. So we are going to have the next class on which day?
Sir,
Tuesday.
Tuesday.
Yeah, Tuesday regular class we'll have, and Friday we'll have a regular class. And remember, actually, Kriti, as we discussed, please convey this message to all your friends. And next Saturday also, I would like to have some tutorial